So, hello friends. So, in this tutorial, we are going to understand the finite volume discretization in the OpenFOAM within OpenFOAM. So, basically, we are going to see that what are the main classes that handles the numerics and discretization in OpenFOAM. And then we are going to see that what are the classes which handles the computational domain, and then we will see that what are the classes which generally handles the linear equation system and the linear solvers. Okay, so basically if we see, then OpenFOAM is known as the open source field operation and manipulation, and it is basically based on the object-oriented C++ framework. Okay, because this OpenFOAM is known as the object-oriented programming, so everything that we works on generally rely on the OpenFOAM classes. So that is why it is important to understand the different classes. So if we see, so first the main classes which handles the OpenFOAM, it starts from the numerics and the discretization. Okay, so this is the first important class. Okay, that start from this FVC and FVM kind of the method to handle the numerics and discretization. Okay, so if you talk about like different objects, okay, and then we are going to see that what are the type of data it handles, that we are going to see, and then finally there will be what is the specific OpenFOAM classes which handles these objects here. Okay, so first objects that we see, it is interpolation. Okay, now this interpolation is generally used for the data which requires the differencing scheme. So like in OpenFOAM we can have this surface interpolation. Okay, now this surface interpolation can have a different template. Okay, so different template means it can be like surface vector field or surface scalar field depending upon our field that we are trying to interpolate. Now this second is the explicit discretization. Explicit discretization. Okay, so if we talk about the explicit discretization, so there are different differential operator. So if you see some scalar transport equation, or even if we talk about the momentum equation of the Navier-Stokes, so in those equations you can see that there are various kind of operator is being used. So in some scenario we use this as a explicit discretization, and sometimes we use it as a implicit discretization. Okay, and this implicit discretization also takes the differential operator. Okay, so it can be the gradient term, or it could be the Hessian gradient term, or it could be the Laplacian term, or it could be the transient term. So these are known as the differential operator. Now if we talk about the explicit discretization, so in explicit discretization, generally the terms is calculated at the same iteration. Okay, so what I mean to say that, I think I can explain here in better terms. So suppose we have this kind of a matrix equation. So Ax equal to the B plus C. Okay, so B is also some matrix term and C is also some matrix term. Okay, so I'm not explaining in terms of the partial differential equation, but I'm explaining in terms of the matrix, linear equation of the matrix. So if we see, so when we are going to the next step, so in that scenario, this X, this field is the unknown field. Okay, so we are not knowing the value of this X matrix. Okay, and this B and C, we have some values, so some numerical values. So like suppose it is a 1x3 matrix and this is also 1x3 matrix. So this two matrix has some numerical value. So if we try to calculate the unknown matrix X, then we have to sum up these two matrices, and there could be some, like we can take it as a D matrix. So D is equal to the B plus C. So basically, if we are calculating these operators at the same iteration, then that kind of the operator is known as the explicit discretization. But some matrix we just pass over the iteration to do the next iteration, because we have many terms whose values are unknown in that operator. Okay, so this kind of the operator is known as the implicit discretization. So what I mean to say that, so if we see in the partial differential equation terms, so generally this d dt term is calculated at the same iteration. Similarly, this divergence, in some equation this divergence terms is also calculated at the same iteration. Sometimes this grad terms is also calculated at the same iteration, and similarly this curl. So this, if we are implementing this explicit discretization to this operator, then in OpenFOAM we write it as a FVC. Okay, now this same operator, if we treat it as an implicit discretization, so d2 t2 or divergence and Laplacian, if we are treating it as an implicit discretization, then in OpenFOAM we write it as a FVM, finite volume method, and this is finite volume calculus. Okay, now this FVC and FVM method we can see inside the OpenFOAM. So I am using this version 2306 version, but the logic that is applied to this version is going to work for the, I think, almost all the versions of the OpenFOAM. So within this SRC we have to go to this finite volume, and then we have to go to the finite volume. So there you are going to see this FVC and FVM, and within this FVM and FVC you can see the different implication of this discretization terms in the FVC also, and here you can see the different implication of the FVM also. So now if we compare between the FVC, so you can see that the FVC has a large operator, differential operator, compared to the FVM. Okay, so only this operator you can use for finite volume method, and these are the number of operations that you can apply to the FVC method. So basically this FVC has the large number of operator compared to the FVM, finite volume method. Now if you want to see this main header file, so this basically always contains the sourcing of other header files. So you can see this finite volume method, this has the ddt term, d2 dt header file, divergence, Laplacian, and this SUP, all the divergence schemes are given in the finite value method. So whenever we call this fvm.h folder, fvm.h file, so it will automatically going to recall all this header file. Okay, so again we can see this DDT. So here you can see the declaration of the classes. So this is like the way you can call this DDT, and you can see that all type definition has been defined here to call this DDT term. So here the declaration is given, and similarly if you open the C file, so this C file has a, so this C file you can see that the class definition. Okay, so how this DDT terms can be called up, and how the discretization of the mesh is done, that all is written in this .c file. Okay, similarly you can see for the divergence term, Laplacian terms, and like d2 dt square term. Okay, and similarly if you go to the finite volume calculus, so we have slightly different treatment here. So this is the class declaration, and here you can find out the definition. Okay, now the second type of classes is known as the computational domain. Okay, so we have now discretized the different operator. So these are the classes related to the operator, and this surface interpolation is left, and I think you can also show this different interpolation in this folder within the finite value. So there is a surface interpolation and other type of interpolation. You can see that here also there is a volume point interpolation, and there is also, you can see that other type of interpolation. Okay, but if you talk about the specifically that finite value method for the CFD, and specifically for the simple Navier-Stokes equation, so generally we are going to use this surface interpolation. Volume point interpolation is basically used in where we require this FSI kind of the treatment, but if you are working on that direction, then you can also go through it. So let's see this other type of the computational domain. Okay, so we have now done this operator discretization. Then we can see that how the variables and the mesh is being handled within the OpenFOAM. Okay, so again we can have this objects type of data in OpenFOAM class. So we can write it as a type, and then again we can have a type of data. Okay, sorry, here it could be object. So what type of objects we are handling, and what kind of data this object is going to handle, and what are the OpenFOAM class which handles this type of the data. Okay, so first is the variables. Okay, so first objects that handled by the OpenFOAM are the variable. So basically these variables, whenever we have started working with the C++, we have come across this different type of variables, like primitive variables. We call it as a primitive variables, and these are generally the scalar quantity, vector field, or tensor field. Okay, so these are the general variables that we are studying from the start of our first C++ tutorial classes. And then this comes the mesh components, because we cannot work with the CFD without the meshing. And in OpenFOAM, this mesh is handled using the faces, points, and cell concept. Okay, and I think you already know the difference between the point, cells, and faces. So in OpenFOAM, generally the discretization is done using these three major data, that is a point, face, and cell. And if you come across the block mesh folder or constant polymesh folder, so you have seen that there are point file, there is a face file, and there is a cell file. Okay, so OpenFOAM handles these three variables as a point class, face class, and cell class. I think whenever you write any class in OpenFOAM, start writing from the small letter, so that rules you should follow everywhere. So these classes always start with the small, and whenever one word ended, so it should start from the capital letter. Okay, so that is, you can see this surface is the start with the small letter, then after every one word, the word start with the capital letter. So this is the logic that applies to. Then this is the components related to the meshing. So whenever you define a cell on a grid, so this point, face, and cells are there. Now so to do some implementation to the meshing, we cannot every time call this point, face, and cell. So for that purpose, we have defined one class that we call is a finite value mesh. So every time we call this finite value mesh, so this finite value mesh will directly call this computational. So it will call the whole computational mesh. And in OpenFOAM, we can call it as a fvMatrix, and there is a concept of the polymesh. Okay, so whenever we want to call the object of this computational mesh or finite value mesh, we can call it as using the fvMatrix, and this is the polymesh. We are going to see these things in OpenFOAM structure also, but before going to that, let's see that another object, that is the time, and then only this class stores the time database. Okay, and in OpenFOAM it is capital letter. So you should remember that this time is the only class in OpenFOAM which starts with the capital T, as far as I know. I'm not sure that there are other classes also or not. So now let's see these classes in OpenFOAM folder. Okay, so this is src, and if we go to this src OpenFOAM, and within this OpenFOAM, if we see different variable where we can see these variables. So let me search this. I exactly forget. Okay, so we can open here. So you can see that within the OpenFOAM there is a one folder named as a primitives, and within the primitives there are different variable declaration and the relevant function and methodology you can check here. So like if you go to the tensor, so you can see here that there is a declaration of the different operators and functions and methods within this .h, and then there you can find the different, like how this tensor handles the floats. Tensor can be how handles in terms of the list, how you can handle in terms of the integers that you can see here. Similarly, you can look into this scalar quantity. Similarly, you can look into the vector fields. Okay, so this all are like kind of the primitive variables that you can check into the OpenFOAM. Now the second things that we are discussing about the mesh component. So I said that this point, faces and cells are the generally geometric information, and when we want to do some operation for this partial differential equation or differentiation operators, so we cannot call this point, face and cell each times. We have to call this fvMatrix, okay, which is kind of the finite volume mesh information. So basically, if I want to differentiate between this fvMatrix and polymesh, so the differentiate between this fvMatrix and polymesh. So this polymesh is a base class. Okay. So this is the base class. So it start from the geometric definition. As soon as you do the discretization of a given computational domain, so this discretization has geometric information like what is the coordinates of each points and which points are connected to each other to form a edges, then how these edges connected to each other, and these edges form the faces, and how these faces connected with each other and form a cell. This kind of information is called as a geometric information, and these are generally used as a base class. Now this fvMatrix is derived from the polymesh, and that is why it is called as the derived class. Okay, so basically what I mean to say that, so if you go to the OpenFOAM in SRC, and I think here this finite fvMatrix is defined here. So if you open this fvMatrix, so you can see that this fvMatrix is derived from the polymesh. Okay, so this polymesh is the base class and it is derived into the fvMatrix. Now if you want to see this polymesh definition, so you have to go to the SRC OpenFOAM, and within this OpenFOAM there are different mesh definition is given, and here you can find there is a polymesh. Okay, now this polymesh is the base class. Okay, so it of course contains some primitive mesh information and some object registry to store this information into the OpenFOAM object registry, but this we can call as a base class because it handles generally the geometric information. So if you see this polymesh class definition, so there are this information that you are seeing, like we have owner information, we have faces information, we have point information, and boundary mesh information. So this kind of geometric information you can get from this polymesh. But if we see this finite mesh method, so you can see that we are not here calling finite mesh methods. We are generally creating one object which can be used for the physics purpose, for the discretization purpose, for the calculus purpose. So basically what I mean to say that here, if you want to understand the geometry, or if you want to do some treatment related to geometry and topology, so basically this polymesh is better to handle. But if you want to handle some physics or we can say that whenever we say physics, we are basically talking about the differential operator or partial differential equation, or if you want to do some discretization, discretize some terms related to some governing equation. Know that where this polymer is generally being handled. So you can see that I think you have come across this constant folder. So this constant has this polymer, and this polymer is stored in this constant folder. But FVM has property that it has been like created dynamically, and it can be called during the runtime. Okay, so that is why basically in FVM you can see that this FVM can be called during this solver modification or utility modification. So in those scenarios, this FVM object is generally called as. Okay, so basically in one line I can see that. So like if you want to use a utility like block mesh for the meshing purpose, or for the like refine mesh kind of utility. So if we are using this kind of utilities which is particularly related to the geometry and topology, so in that scenario this polymesh is being called. But if you are discussing about the solvers or sometimes the post processing for the field, okay, so like if you want to post process the U field or V field or temperature or other fields, so in that scenario this FVM is being called. Okay, so I think you have understand till here that what is the difference between the FVM and polymesh. Now the last one is this time. So this time is kind of a database. There is no like computational domain kind of thing related to the time. So that is why time is generally stored as a database. So if you go in OpenFOAM, SRC OpenFOAM, and there is a folder known as the DB. Inside this DB there is a different kind of the techniques how we generally handles the database within the OpenFOAM. So like if you have some data related to the dictionary, so you can see this folder. Now if you have some data related to function objects, so you can visit this folder. And similarly this IO object list, IO stream, object registry, option, so these things you can see that. And this is also runtime selection, which is like during the runtime how you can handles the data selection, that you can see in this folder. And this is a folder related to the time. Okay, so then only this time is declared within the control dict, and you can just visit here and you can see that how the different class has been created. So if you visit the control dict folder, so you can come across this kind of variable that write controls, stop controls. Okay, so this kind of things, and you can see that it is being called using this control dict folder. Okay, so these things you can visit here, and you can see that there is a adjust delta t function that is generally we called for transient kind of problem. Okay, and how to write this time step, that is also one function is given here. So here in .h you can find the different declaration related to the time, and if you want to visit for the definition, you can just visit this folder, that .c folder. So now we have understand the numerics and discretization. Then we have understand the computational domain related like mesh and finite value method. Now next thing is that is the field. Okay, so let's see this field operations. So again let's we see some objects. and what kind of the data it is going to handle, and let's say the relevant OpenFOAM class. Okay, so there is the first the declaration of the field. Okay, so the field which is declared here. Now what type of the field values it is going to handle. Okay, so basically in OpenFOAM we defined it as a field and then we give the template here. Okay, so basically at the place of the template it could be the vector, it could be the scalar, or it could be the other kind of the values it can take. Okay, and sometimes the dimensions of the fields is also important here. Okay, so there is a dimension setup. So generally if you see the files within the 0 folder, so there is a one line of information which contains the setup for the dimension, and in OpenFOAM this dimension setup is handled with the class name as the dimension set. Okay, so this is the class that handles the dimension within the OpenFOAM, and again there is the some variable related to the field. This variable field contains the field plus mesh plus boundaries plus dimension. Okay, so this whole recipe gives the information for solving one type of a governing equation, and this whole information is categorized as the variable field, and in OpenFOAM we called it as a geometric field. Okay, so of course it could have some template. Okay, so what I mean to say that whenever we want to do some field operation, so for that field operation we generally call this geometric field, and whenever we call this geometric field, it means that we are calling field associated with a mesh, and this mesh has the boundary condition and this field has some dimension. Okay, so as soon as we are going to call this geometric field, so this geometric will automatically have this type of information. So this geometric field has automatically field mesh boundaries and dimension. Okay, so that is why while we do treatment sometimes, and this kind of error we are going to see that this geometric field should have this type of a dimension, or this geometric field has like mesh is the missing. So this kind of error whenever you see related to the geometric field, it means that you are either of missing information from this four types of data. Okay, now once we have defined this variable field, then we have of course this operation, algebraic operation. Okay, and this equal sign, then of course this sine, cos, and there are lots of algebraic operations are there. Okay, and these are known as the field operator. Okay, so basically if you want to write, so we have first we have this polymesh. Okay, then after this polymesh, we have this FVM, and then after this FVM, because without mess we cannot create the fields here. Okay, so without messing we cannot have a field here. So we have this field template which is defined on FVM, and of course as long as we have this messing, so at the same time we should have a like boundary fields, and of course there should be a dimension. And once this all this FVM field, boundaries and dimension is defined, so automatically we will get a geometric field. Now whatever the template of this field is there, that is the same template applied to the geometric field. Okay, so I think you understand this logic here, from starting from the polymesh to the geometric field. Now let's see this same logic within the OpenFOAM. So if we see this src folder of this OpenFOAM, and if we type this field, okay, so we can see that at this location the different type of the field definition is given here. Okay, and within this field, okay, so if you open this folder, that is the field.th, so you can see that the definition of field is given here. Okay, and you can like the declaration you can see at this .h folder, and similarly you can go and you can see the different definition of this different function and method in the .c folder. Now one thing you can observe that here there is no any information is given about the mesh at this stage. Okay, so here just the declaration of the field and the different functionality of the field is given here, but at this stage there is no any kind of information related to the meshing or dimension is given here. So you can see that this is the order of the dimension which is defined within the OpenFOAM. So start from the mass, then length, then time, then temperature, moles, current, and luminous intensity. Okay, so basically this is the standard standard order to handle the dimension, and this is also defined within the OpenFOAM. Okay, now again there is no any relation of this dimension set class related to the field or related to the mesh here. Okay, so you can see that there is no any kind of the declaration of the field here or any kind of the declaration of here. Okay, so till here the field is a separate set of the class, and then this dimension set is a separate field of the class. But as long as we enter into the geometric field, okay, so we enter into the geometric fields. So if we go to the geometric field class, okay, so if we open this .h file where the declaration of the classes are given, so if you see any constructor here, okay, so first of all let's see that how the this class has been declared. So you can see that the template of this field is recalled here. Then this template of this patch field is which is going to handle the boundary patches. It is also being called here, and that is the geometric mesh information that we discuss earlier that this geometric mesh is derived from the polymesh, and this geometric mesh handles the geometric information or topology information of the meshes. That is also being called here. Now here this dimension field is also called here to handle the dimension of the different fields. So you can see that now this geometric field class is taking care of the field as well as the mesh, as well as the boundaries, as well as the dimension set. Okay, so now this geometric field is something where we start doing the field operation or doing the physics or doing this calculus things. Okay, so that is why this geometric class declaration is important to understand. And you can just go there, and you can see also, if you go at the little bottom, so you can also find the different operators that we have discussed here. So this multiplication, subtraction, and equal to sign, and division. So this different type of the operator definition you can also see there. So we have this geometric field definition, and once we define our geometric field, then we can discuss about the linear system equation, because finally we solve a matrix. Okay, and matrix is kind of a linear equation system, or we can say that the linear solvers. So let's see different classes related to the linear equation system. So basically we are going to see that how this OpenFOAM, what are the different classes which handles the matrices here. Okay, so let's see that what are the different objects and type of data, and then finally what are the OpenFOAM class. Okay, so basically first we should know that how this OpenFOAM handles the sparse matrices. Okay, and when I say this sparse matrix, then I mean to talk about the matrix coefficient and manipulation. Okay, so in OpenFOAM there is a class known as the lduMatrix and fvMatrix, which handles the matrix coefficient and how it can be do the manipulation on those matrix coefficient. Okay, sometime, or we can say the most of the time, we do this iterative solver, and for that purpose we have this iterative matrix solver. So this we have to handle the matrix during the iteration for a solver purpose, which handles this solver. Okay, so there is one method within this lduMatrix which handles this iterative solver. Okay, so we also need to do the preconditioner to the matrices. Okay, and this type of operation is known as the matrix preconditional. Okay, so basically this is the two important matrix, that is the lduMatrix and fvMatrix. So if you have come across some solvers like SimpleFOAM or other kind of solvers, so you can see we have seen this fvMatrix. Okay, now let's see within the OpenFOAM. So this fvMatrix is kind of a high level class. So this fvMatrix creates a bridge between the physical equations and our underlying algebra. So what I mean to say that, so suppose we have this solvers, and we can take any solvers, like let's say this simple Laplacian equation. So here if you see, we are trying to create here this FV scalar matrix. Okay, so this is kind of this FV matrix that we are creating. Okay, now if we see within this OpenFOAM, so within this OpenFOAM there is one folder that is fvMatrices, and within this fvMatrices we can see this method, this fvMatrix dot h kind of folder. So here you can find out the different operators and different methods related to this matrix. Like if you want to take the scalar diagonal out of this matrix, then you can use this d methods. You can also calculate the residual of the matrix, and you see that this t equation dot solve, this method is being called from this matrix where this function is declaration is done. So here you can see that in fvMatrix dot h this solve method is created here. Okay, now the lduMatrix is kind of a low level class definition. Okay, so basically it creates all the algebraic structure of the matrix. Okay, now here this fvMatrix is creating a matrix, but how this matrix is structured and what are the different methods and function related to this matrices, this kind of definition is defined within the lduMatrix. Okay, so now in lduMatrix there are like how this OpenFOAM stores this matrix using the different format that we can discuss here, and that is very important concept. We have our partial differential equation or physics equation, we can say. Now after PD, this PD would be converted into the FV matrices. Okay, so like using this like different discretization terms of FVM or FBC. Okay, we generally discretize this Laplacian term or different discretization operators, and it also handles the boundary condition. Okay, and of course it has dimensions also. Okay, as we discussed earlier. So this fvMatrix just creates the bridge between this matrix and this partial differential equation. Now if we take an example of the matrices, let's say 3 by 3 class matrix. Okay, so like we have some, suppose we have some scalar transport equation, maybe the temperature equation that we are discussing. So this equation is converted into the form of some Ex equal to the B. Okay, so this is a form of the equation that is converted. Now this equation A, the matrix A can be written into the 3 by 3 matrix, and here there is a diagonal components, and there is component which we can't call this as a upper diagonal components, and there could be some lower diagonal components. So this lduMatrix of the OpenFOAM handles this lower diagonal components as L and these components as U, that is the upper diagonal components, and then it takes this diagonal components as a D. Okay, so this is how this lduMatrix handles this different coefficient of the matrix. Okay, so there are 3 is important components, that is the D, L and U. Now once we have this lduMatrix, then we can do this lduMatrix and this solver iterative method that we have discussed, and similarly we can also do this. Preconditioning. So this is the structure of this fvMatrix, lduMatrix and lduMatrix solver and LDU precondition. Now let's see that where this lduMatrix stands within the OpenFOAM. So if we go this OpenFOAM src OpenFOAM folder, and here if you go within the matrices, so here within the matrices you can see there is a lduMatrix. Okay, now within the lduMatrix you can see these solvers. So generally the iterative kind of the things like different operations related to the matrices during this iterative processing, that is generally stored within this solver folder. Now this preconditioning, that you can see that we also apply this preconditioning within the FB solution folder files of the system, and this preconditioning is definition you can find here only. Okay, so this you can visit here and you can see so if you see here that we were discussing that there it handles the D component and this U components and diagonal components. So you can see that the different coefficient has been written, this lower coefficient and diagonal coefficient and upper diagonal coefficient. Okay, so basically this matrix, any kind of the matrix, it is handled by this lduMatrix, and lduMatrix creates the database of the coefficient in the form of the three function, that is the lower, diagonal and upper matrix. Okay, so I think you have now a better idea about what are the main classes related to the OpenFOAM and how these classes is being handled within the OpenFOAM. So this is our first class where we are going to learn OpenFOAM in the different way, in from very different perspective. So I would stop here because video duration is already too long. So I will just start from here in the next tutorial. So thank you for watching my video, and I think you like this content because I'm trying to create the contents, OpenFOAM contents from completely different perspective. So please subscribe my YouTube channel so that you can get notification of my new video on this session.